In this problem, we're exploring this notion of equivalence, and equivalence as applied to both a force kind of analysis and a moment kind of analysis. So the physical system we've got here is some sort of a pole which is acted upon by a few different forces, and our goal here is to replace the system of forces that you see in the figure by an equivalent resultant force and couple moment up at the top of the pole at point P. So the approach here is actually fairly straightforward. There's not a lot to it when we write it out in terms of steps, but there are some subtleties that you'll see along the way that we just have to pay attention to. Let's go ahead and write an approach. So there's really only two pieces to this problem. The first part of the approach is to find the resultant force, Fr, and the second part is to find the resultant couple moment, Mr. And this is going to culminate at the end with a sort of a sketch of what this looks like. But you can think about these equivalence calculations as being sort of like vector summations. And as you'll see as we go along, these vector summations follow the typical rules of vector summations. We just have to be careful with the usual things like angles and sines and the like. Let's go ahead and get started here by looking at the coordinate system and the geometry. We notice that this is a planar problem. We've got a right-handed coordinate system, x off to the right and y vertical. And we've got an angle here that we have to solve for. Let me switch to red. So this angle right here, we can write an equation for this angle as theta is the inverse tangent of 3 over 4. So this just equals 36.9 degrees. And that's going to come in handy as we start to define some force vectors. Okay, let's go ahead and start with step 1. I'm going to start on this page right here. Step 1 is to find Fr. So in order to do that, we have to define what Fr is going to be in terms of these other forces. And so if I call, let's say, this one F1, and if I call this one F2, and if I call this one F3, then I'm able to write that my resultant equivalent force Fr is simply going to be F1 plus F2 plus F3. That's our definition of equivalence. Okay? So on this page, I'm going to write F1 and F3 because those are going to be easy to write in terms of our coordinates, and then on the next page, we'll go ahead and write F2. So F1 is a force of magnitude 30 pounds in the negative y direction. So F1 just turns out to be minus 30 in the j direction. That's units of pounds. And then F3 is equal to 40 in the I direction, also with units of pounds. So those two are pretty easy. What we're going to do with F2 is kind of project it into x and y components, and we'll do that here on the next page. So F2 turns out to be a magnitude of 60, and then it's got a minus sine of 36.9 in the I, so that's in the negative x direction, minus cosine of 36.9 in the j direction, also units of pounds. So what we're going to do then is we're going to add those all together and do the math, and if we do that, we get Fr equal to 3.97 in the I minus 78.0 in the j. It's got units of pounds, and we can actually express this in a different way if we want to. We can express this in terms of a magnitude and a direction. Let me draw a small sketch here to indicate what's going on. So if this is point P up at the top of the pole, the vector Fr looks something like this. Okay, it's got a small piece of the vector which is going in the positive x direction, and it's got a much larger piece in the negative y direction. Okay, we can find the resultant force, which is the square root of the sum of the squares. So Fr resultant is equal to 3.97 squared plus minus 78 squared square root. That turns out to be 78.1 pounds. And then the angle theta, let me define it this way. Theta equals the inverse tangent of minus 78 over 3.97. This is just minus 87.1 degrees. Okay? Now, I guess I should be kind of clear here. I included the negative sign here, which leads to this negative sign here, even though I defined theta as sort of this clockwise direction. Really, this minus 87 degrees is corresponding to a theta which is positive in the counterclockwise direction. You can define it any way you want to, but you have to be careful about how you carry the signs around. Okay? And so we know what direction it's going to be because we can draw the picture, and we just have to make sure that our calculations tell the same story with respect to that angle. Step 2 then is to find the moment resultant, mr. And so the way we're going to do that is we're going to sum up the moments due to each one of those forces. So our mr is going to be m1 plus m2 plus m3, where m1 is equal to r1 crossed with f1, m2 is r2 crossed with f2, etc. So let's go back to the picture and figure out what those r's are going to be. All right, so here is the point at which we are going to define the moment. That's up here at point P. So that means one of our r's is this one right here, and one of our r's is that one right there. Now I drew it off the axis just so you could see it. This one is r2, this one is r3, and what do you think r1 is in this case? Well, since the force F1 goes directly through point P, R1 is just equal to 0. You guessed it. All right, so let's go back out here and start writing what these R's are going to be. We just decided that R1 was equal to 0, so that means that M1 is equal to 0. M2 is going to be R2 crossed with F2, and R2, according to the figure, is minus 1 in the j direction, and that's going to be crossed with F2, which is 60 times minus 36.9 in the I, minus, made a small mistake there, minus sine of 36.9 in the I, minus the cosine of 36.9 in the j. So M2 turns out to equal to minus 36 in the k direction, has units of pound inches. Okay, so the j crossed with the j goes away. And then M3, that's going to have an r, which is minus 4 in the j, according to the figure. And then we're going to cross that with 40 in the I direction. So this turns out to be plus 160 in the k direction, pound inches. So when we do the summation, mr turns out to be plus 124 k pound inches. Okay, so there is our result for the moment resultant. And what I want to do is go to the next page and just draw a quick sketch of what this all looks like. So if this is the top of this pole, somewhere like that, let's say this is point P, we've got the force resultant operating down this direction somewhere, FR, and we know that that is at an angle of 87.1 degrees. And then we've got the moment resultant acting in the positive direction, which is the counterclockwise direction, because remember our right-handed coordinate system was x and y. Let's go back to the beginning and review. So we have this problem where we're introducing the idea of equivalence in both a force and a moment sense. We know that the equivalent force is basically sort of a vector summation of the forces acting on the structure. When we go through and do that, we found out that that vector had a magnitude of 78.1 pounds, and we had an angle of 87.1 degrees in the clockwise direction with respect to the horizontal. Then we did the same thing for the moment, which was basically the summation of the moments of each of those forces. Came out to be 124 k pound inches. And a sketch of what's going on here. This is how the moment and the force act at point P.